training course for independent auto techs. The idea being to get them up to speed on hybrids so they can fix people's Priuses that are now falling off of warranty, especially the classic ones and now the 04s and as they go forward. So what I've been doing is actually printing up pointers to the training slides site. And I'm going to have to kind of whip through this because this really is kind of like 10 hours packed into one. I've been actually going around handing these to auto techs and pointing them at these slides, which I just put up for free because the seminar thing wasn't really working out. I was kind of thinking, well, you know, we're never going to get this off the ground, so I still want to get this information in people's hands. So, and there's also a link to it off my main site, which a lot of you know where it is. So, as part of that, you know, I'd sort of introduce myself and you know, who's this nutcase running around in bare feet telling me about hybrid cars when he doesn't even have ASE on his sleeve. Background is, you know, just sort of hobby electronics all my life, and you know, I was at a vehicle hacking when I was doing the lift kit truck with big tires thing back in the 80s and stuff. So the Prius really brought all of those fields together, and in fact, the Prius brings a lot of really nice technologies together because of all of the different industrial motor control and whatever involved in its design. You've probably seen these flyers. What I hand out to people, like just on the road. You know, I'll occasionally just stick these in the door handle of the Prius. You know, spreading the word is there's, you know, we all know the really strong sense of community. The auto techs may not be aware of this. So the fact that we're all talking amongst ourselves on these forums and things is maybe a little bit new to them, although they're familiar with enthusiasm. My big thing that I've done in my car is instrumentation. So the actual operation of the car is unmodified, but I've tapped a few lines here and there for useful inputs like you know, tachometer for the engine because they don't provide one, battery current meter. Those are like the two basic things, and I put a bunch of other stuff in as well, just as I saw a need, and added it to this panel. And I think driving barefoot helps. It makes me actually feel safer on the road and have finer control over things. And you know, the early results from running around with that early instrumentation kind of spoke for themselves. It was, you know, came back from a run with this going, you know, nobody else on the forums had spoken of anything over, you know, 60-something. I was like, wow, I'm going to really kick ass at Tour de Sol this spring. And little did I know that other people were already pushing the 3-digit boundary. I hadn't found those people yet. So, you know, for the first year of ownership or so, I ran around with not this much of the dash torn apart, but a good bit of it. People look at it and wait, you just bought this car, right? The last one that went missing.
That's how I got it.
That's how I made it go. So, as part of educating the auto techs in all this, we have to sort of bring them up to speed on a different way to think about the cars. You know, and the fact that Toyota really did a good job on ease of use. You put it in D, you go, and you don't have to think about anything else. But at the same time, there's all this stuff going on under the hood that's just really fascinating, and they're going to have to come up to speed on it. So, you know, teach them which car is which, so they can identify the things and, you know, the years of manufacture. All the stuff in green here is things they're going to have to start thinking about, which they may have never seen before. So we have like large electric motors for propulsion. We have hybrid controllers, inverters that sort out all this high power electric drive. Big honking relays that Wayne talked about to connect the big batteries. And we also have no alternator in these cars. We have this DC converter which keeps the 12 volt alive. What the techs may have seen before is shift by wire and accelerate by wire. They've started to see that in other cars. And of course, braking controller by computer, that's ABS. So we have a sort of an extension to ABS in these cars. Talk about keys. Bottom line, if they just turn off the smart key as they bring these into the shop, it's a lot less confusing. Smart key, of course, is not unique to the Prius. It's showing up in all the other cars at this point, too, because people love the thing. You just walk up to the door and the thing opens for them. But, you know, if a customer brings this car in, they swap positions, the tech sits down in the car, now he can't start it or drive it because he never saw a Prius before. This does not look very professional. So we start them on the very basics. The valet cards that come with the car have the basic 1, 2, 3 that you could, in theory, give to anybody and they could get going on it. But then we go into the more complex states of starting the thing. You know, it's kind of like the key. You have off, you have accessory, sort of run position and a start position. And this has a pretty close correspondence to that, although what happens in each stage is a little different. We challenge them to find the one wrong arrow in this chart by the end of the day. Same thing for shifting, especially in the second gen Prius, that little paddle shifter. Anytime you go into neutral, as highlighted here, you have to worry about that little half-second delay. So they're going to be unfamiliar with that sort of thing. There are subtleties that are useful to the auto tech. If they want to just get the engine running, they can put it in park and push the gas down, and it'll start up and run up a little bit. And if they want to just get it to idle in base idle at 1,000 RPM, the trick there is to get it running and then shift to neutral. And the definition of neutral in these cars is thou shalt not touch the electric motors. That's all there is to it. And a side effect of that is you cannot start or stop the engine, so it stays running or it stays off, depending on what state it was in. So at this point we're up to, there were a lot more slides packed into here, but at this point we're at maybe 10:30, it's coffee break time. So we get everybody up out of their seats and go out on the parking lot where we in theory have all these hybrids parked and ready, hand out keys and say, go play with the cars, go learn them, go start them, drive them around the lot, learn those different states and things. When we come back in, we transition from the customer level to the tech level. And the first thing we have to think of is shop safety. And at this point, we start going into the whole high voltage thing, bring them up to speed. To condense many, many slides into one, we talk about what kind of currents it takes to hurt, tingle, lock your muscles, stop your heart, etc. Some of the tools they're going to need. They need certain high voltage gloves, and even the meters need to be rated at 1,000 volts or better. They usually have good fluke meters already, but if they haven't bought those for their shop, they should start thinking about that. And in general, we encourage just keeping your wits about you, just like a household electrician would when they're working on stuff, and not become our safety poster boy here. Except Wayne was doing this all morning, but this is a guy, wearing a watch with the live bus bars and a live pack, and then, all he's got to do is bridge 2 places on that thing, and he can have a bad time. Talk about safety plugs and the basic circuit that it does. It breaks the pack in the middle. It sort of shows what Wayne was showing, but schematically. And we also point out that the whole bus is isolated away from the car's chassis. It has to stay that way, but there's a circuit that detects any kind of ground leak to the chassis, and if it sees that, it shuts the whole system down, because that means something's damaged along the path. Of course, anytime you have an energy supply from the back of the car to the front of the car, it's generally run along the outside of the passenger compartment up next to the frame rail. So gas tank, fuel lines to under hood, battery cables to under hood, same thing. So if you kick those lift pads a little too far underneath, you wind up crushing the cables, and that's a bad time. Definitely point them at the manufacturer sites for all of the hybrids, all the different ones, have these emergency response guides for first responders in accidents. Not only do they go over all the safety things of the car, including batteries and airbags and fuel tanks and stuff, they're a nice tech overview of the car. So they should just read those to get familiar with the cars. We give them a whole page of web links and stuff for these things. The bottom line is, in all of these, is you kill the 12-volt system, it takes down the fuel pump, it takes down the battery relays as well. So unless the pack actually got damaged in a way that somehow froze the relays on, generally, if you kill the 12-volt system, you are quite safe on the car. And these responders that say, "Oop, hybrid won't touch it," are really need to be re-educated.
I thought we said we didn't need the 12-volt battery when it was on.
If you kill the 12-volt system, in other words, power the car off,
okay,
that's what we're getting at here. But some safety trainers say, take your Sawzall and cut through the 12-volt cable to make sure it can't possibly reconnect. It gets kind of extreme about it. Basically, if you're having the key in your hand, the car is disabled. When they finally start seeing these things in the shop, we go over a few things. That's my baby up on the lift there. Maintenance schedule, they're not going to be doing that frequent maintenance on these, even basic things like tire rotations and oil changes. They're not going to see them any more often than 5,000 miles, where the usual thing is 3,000. But when they do, they need to use all the right stuff, and obviously the right oil. The hypermiles are going to come in with their things of 0W20 and say, put this in instead, don't overfill it. In general, since for the aftermarket fluids and things, there's really no genuinely compatible thing in the aftermarket that we can detect that's been time proven. We say, go to the Toyota parts counter and get their fluids and just use that stuff to be safest. We'll teach them a few things about the tools they'll need, the scan tools. They can go for the $4,000 Master Tech unit, or they can try to go aftermarket. They can use their own judgment on that. First thing you do if you have anything that looks like a computer problem, you want to check that your 12 volt is healthy. That causes a lot of problems. Like you were saying about the 12 volt batteries cause a lot of things to whack out. If they want to get into diagnostics, to show them how to hunt down the ECUs under the right side of the dash so they can start back probing things and pull signals out like cam sensors and whatnot. Teach them about the oil reset dance. When the light comes on at 5,000 miles, do the hold down the button and power up trick. That's common to a lot of new cars. They're all having these sort of oil change reminder light things, and there's usually some chicken dance to reset them. One useful thing in the shop is being able to power down a car and still have it in neutral, so that you can push it out of a bay and get another one in there if you need to, if you're in the middle of working on one car. So this, by pulling this relay, they can leave the car powered down without the parking pole engaged, which usually self-parks when you power the thing on. This allows them to leave it in neutral, push around the shop, and the car kind of complains about that because it really wants the parking actuator to work right and detects whether it does it or not.
What's the name of that one, Hobbit?
Which?
That relay you're supposed to pull, what's the name on there?
Pecan motor, according to that.
Okay.
The arrow is from the indicator and the thing to that same relay.
What's the procedure for that? You have the car on and you pull
You have the car on, you pull that relay out, right, and now that disables the whole parking pole actuator motor system.
Then you turn the car off.
And immediately detects that and starts complaining on the screen, but it tells you to set the parking brake, and then it'll actually allow you to power the car off. And it'll actually keep that as an error state for the next few reboots, but you can clear that once you get everything back together.
So you can roll the car around.
Yes, you roll the car around when it's dead. 12 volts all torn apart at that point. Give them a few service specs with a caveat that they should look this stuff up and make sure. And then we're out of the seats again. We go out and play with the things. Maybe start bringing them into the bays, get them up on the lifts to actually have a look underneath and take a tour of the things. We've also gone over the safety plugs and handed out 1,000 volt gloves and had them go after the safety plugs to see how they work. But that's, what we do for the tech training is not what you came here for. You wanted to know how the car works. Starting with a quick review of hybrid topologies. Series hybrid, we have an engine that does nothing but turn a generator, generate power, and then that power is sent through a bunch of power electronics to push a large motor that pushes the car. The advantage of a series is you can motor along an electric only using battery until you need to recharge it. Our theoretical Chevy Volt. Parallel hybrid, this is the Honda topology usually. Smaller engines, smaller motor generator, they can combine forces and push when you need acceleration, but since they're kind of downsized, they're more efficient. Downside of this is you can't go along under electric only, despite Honda's claims that you can, except that you still have to turn the engine. These are sort of linked together all the time, basically as the flywheel of the motor, or the engine. What they do is some kind of valve trick. So Toyota decided to try and get the best of both worlds with a series parallel topology. What we have here is the engine and the large propulsion motor in play here. In the middle we have this thing called a power split device, which is really nothing more than a single planetary gear set, and which acts kind of like a differential. So engine power comes into this and splits out two ways to these two paths. The majority of the engine's power goes through this thing and right out to the wheels. So it's a very efficient direct mechanical path for the engine. The remainder goes out the other side of the power split device, gets picked up by the smaller motor generator and dealt with electrically. And what closes the loop for this whole thing is the fact that these two motors can shunt power to each other through the inverter and in either direction. So depending on various road speeds and torque requirements or whatever, the hybrid computer and the inverter sort out which way power flows there, and the whole thing combined sends some power this way, some power mechanically, and you'll end up pushing the car usefully and charging the battery at the same time, and all the shunting of power around is just figured out by the computer. And planetary gear sets are nothing new. The Model T Ford had a two-speed planetary in its transmission. And any modern automatic transmission has a lot of them in there. This is what it looks like in real life. This is Toyota's standard trade show cutaway. Large electric motor out here. The smaller ones kind of sandwiched in here. These are their poles cut away. In the middle we have the power split device, which is the planetary set. And coupled together sort of through the outer part of that planetary, the large electric motor and this drive chain, which picks off mechanical power and sends it over the back to the wheels, are permanently linked together. So that's how we drive the car on pure electric. The big motor pushes, sort of goes through the outside of the planetary system and then pushes the wheels. An easy way to remember MG1 versus MG2, which always gets people confused, is 2 is larger than 1. This is what the transmission sort of schematic representation. This is all there is to it. There's nothing else really involved here. It's a little confusing in this diagram. I really need to do another one, but the engine shaft here in purple passes all the way through the middle of the unit, ends up in a little oil pump. And the 2 motor generators run on sleeves around that, but they can turn independently from the engine shaft. And these sleeves are important because they can take a connection from MG1 all the way through the middle of this to the sun gear of the planetary system, in this case. And in MG2, this sleeve expands out to also connect to the ring of the planetary, and then also to the sprocket taking the chain drive away. So at the point of where that chain drive takes off, there are 3 concentric, independently rotating parts, which the engine shaft in the center, the sleeve carrying MG1, and then finally the chain sprocket. The torque split in this device is 72% of it goes straight to the wheels, like it showed earlier, and the rest of the 28 goes back through that sleeve's MG1. And all of it stays permanently linked. There's no mechanical shifting at all except for that parking actuator. This is what it looks like in real life. And this is what it looks like in real life. Here's the sleeve that MG1 runs on. This is only half the transmission here. And I guess when this is mostly over, you come up and actually look at this in the light. The other half is missing is where MG2 sits. That's this bigger part here, which would bolt on. That was just going to be too much to bring. But what he's holding, what this is, that's the engine shaft, and it goes all the way through the middle of the unit, and the engine would be on this side of the transmission. The rest of all this gearing here is simply the reduction system from the big electric motor down to the wheels. It's 411. You say the Prius has a 411 rear. That's how it finally gets power to the wheels. Another view of it. Once it's all together, you can't actually see the planet gears at all. Because the basket that comes from MG2 covers all of that too. These rotors are very magnetic, and some of the training things, when we finally got the transmission apart, the tech would hold up the MG1 rotor or something and to look at it and show his buddies. And he had his hotel key in his shirt pocket. He did not get into his room that night. These things are generally really reliable. Toyota considers the entire transaxle replaceable unit. They're not going to really get in here. But paradoxically, the repair manual has complete overhaul instructions. So go figure. If you had all the right sealants and stuff and ways to measure the clearances, you could rebuild these things. And the opportunities would be rare, but maybe some people will do it. Simplest possible representation of the driveline. Again, we have the ring gear around the outside. 2 out of the 4 gears in the planet are represented here and just connected by a simple stick. And the sun gear in the middle. Now, at any given moment in time, a gear train can be represented by a system of levers and pivots, and that's how you figure torques and ratios and things. Since it's a 3-component system, if you know the speed direction of any 2, you can predict the third. It's this fixed relationship all the time. And it can be represented by this fairly simple chart called a nomograph. Down the left side, you read RPM for any of the components, from 0 to plus large and minus large. So down the left side of the chart, we read any of this for MG1. In the middle here is the engine RPM, from 1,000 RPM up to 5,000 or off. So there's a discontinuity in that. And again, you just map the RPM right over to it. For MG2, we read it down the right side of the chart, again based on RPM. But since MG2 is also connected right to the wheels, it has a direct relationship with road speed. So here's a translation into road speed for MG2. So you can actually read, if MG2 is spinning at 3,000 RPM, you're doing 50 miles an hour. And so when you draw a straight line between any of those points, that's how you predict where MG1 is in its rotation. So for instance, if you're tooling along at 20 miles an hour in EV mode in a Prius, and the engine is off, sitting at 0, MG1 is spinning at minus 3,000 RPM, and that's always got to be true. You can't get away from that.
Does that chart go, what was it? the kid got pulled over in a Prius doing 100, doesn't look like you could maybe get there, or
Well,
you'd have
if
to
he's,
go
if he's doing
way up?
105 with the engine at like max RPM, right?
Okay, So you
MG1
put
is
down
going to be at
the-
a fairly modest RPM,
okay.
and it's going to be trying to hold that engine back. One way to think of this is if I have two shopping carts in front of me in a parking lot, and I want to push both of them, I have a broomstick in my hand. I can put the broomstick behind both carts and push in the middle. But now somebody comes along and fills one of the carts with cases of soda, so it's much heavier. And if I push in the middle of the broomstick, the empty cart's going to shoot ahead. To balance that system out, I have to move down to one side of the broomstick and push somewhere with an offset. You know, and then that's where you see that sort of offset. So MG1's job really is to charge the battery when you're sitting still, start and stop the engine, and pick up all of the slack torque in this system between the engine and the road. MG1 has to grab that at sort of the other side of the power split device, deal usefully with it, and and then it's going to be sending energy off to the bigger motor to help push or charge the battery, or a little of both.
Hey, before you jump off, now that I'm looking at negative rotation, does that mean it's spinning
Yes,
backwards?
MG1 spins backward on a regular basis.
Okay.
And in fact, just about any motion with the engine off, MG1 is always going to be spinning backwards. If you draw a line between any positive road speed and engine off, you're always going to wind up with negative rotation in MG1. So it just sort of freely goes back and forth both ways over this large continuum. We'll get back to this later. Once we turn the lights on, we can come up and look at this thing. A few things about the engine. I mean, we have this wonderful hybrid system with the electric motors and stuff, but we still have to burn gas at some point. Meet Torquey the Muppet. This little guy is good for 50 or better miles per gallon by himself without any of the hybrid system wrapped around it. It's a very efficient engine. They've done all kinds of efficiency hacks to make this thing very low friction. So it's based on the 1.5 liter Echo plant, but even in that they have things like an offset crank, so you get a more straight down power stroke. They use lower oil. They have low tension piston rings. I mean, you can reach in there. If you get your hand down next to this engine, you can grab the pulley and actually turn it with one hand. Try that with most engines. This thing almost feels more like a lawnmower. But the major thing, of course, is the Atkinson cycle intake timing. If you notice that the cam lobe on the intake is a lot fatter than the exhaust. Back in Merry England, a guy named Atkinson came up with this engine which physically changed the displacement of a piston every other stroke. And the idea was to pull in a little bit of mixture, compress it a little bit, and then extract all of the energy from the burning gases on the power stroke, which was much longer. So what this gives you is significantly improved fuel economy at the expense of a little bit of torque, especially at the torque peak. Later on, a guy named Miller in this country realized that he could do the same thing without all the complicated linkage by simply delaying the intake valve close. So I'm going to wave my finger like this a lot to sort of represent where the crank is in the engine. Most auto cycles would close the intake valve about here. They'd suck in a full charge, close the intake valve, and start compressing pretty much from the bottom. So the compression ratio and the expansion ratio are pretty much the same. In this thing, we don't really close the valve until about here, or we couple that with variable valve timing, and we can change where we close the intake over a fairly large range here. So now we're just compressing a little bit over the top and getting that full expansion burn. The side effect of that is that as we pulled in a full charge of fuel, now as we're not compressing yet, a little of that has to go back out the intake valve into the plenum and kind of hang out and wait for the next cycle. So that's what it does. It just pushes it right back out into the intake, and it'll get sucked in on the next charge. Obviously, when techs do compression tests, these cars are going to be lower because you're not getting the full compression ratio. It's got a whole bunch of different modes based on the valve timing. The two most important ones are fully retarded when we're idling the engine, starting it up, or in warp stealth, where we actually retard the valve timing and get very, very little pumping loss. When you're screaming down the highway at high speed, you're still spinning the engine in fuel cut, but it's a very low friction state to be in. And the other mode is more advanced, where we actually want the sort of low-end grunt torque out of the thing. The more compression you get, the more torque you get out of the engine, but we don't get it too extreme about it because we still have the Atkinson timing at play here. The other thing to notice about the sort of range 4 that I talk about, at the top of the exhaust versus intake stroke, we have a little bit of valve open overlap. So both are open a little bit, and the exhaust gas can kind of mix up with the intake gas a little bit. What this gives you is internal exhaust gas recirculation to keep the NOx emissions down. And it's all done inside the cylinder. So suddenly all of that plumbing, the EGR plumbing that people are always fighting with and having to scrape the carbon out of, just went away. It's not in this engine. It's all done internally. So that's a really nice side benefit of any kind of variable valve timing. That's starting to show up in other cars as well. Interesting side effects from that pushing the intake back out. An oil sump seems to always show up in the bottom of the intake in the Prius. It's sort of just a layer of this thing, this stuff that looks like oil in there. There are several theories. Some of it is PCV gases coming back from the crankcase, and the other theory is that because you're pushing some of the mixture back out, the heavier elements of the gasoline may just fall down there and then not be able to be vaporized. Nobody really knows. It doesn't really smell like oil. But the bottom line is that little skin is always there. It's not, you don't really have to worry about it. But sometimes the throttle bodies on these cars tend to crack up. There is some amount of oil and other stuff floating around in there, and it can collect on the edge of the throttle flap and actually stick it shut in some cases. Since the throttle flap is operated by a motor, not the driver's foot, that motor doesn't quite have enough torque to unstick it and get it open. That can cause problems, especially in cold weather. And last November, classic Priuses were dropping like flies with the same complaint. And the simple answer is to simply do a throttle body cleaning, and that's a service that mechanics often offer anyway, so it's important in these cars. So here, Torquey's really got to go here on an oil overfill. You get up above the upper mark on the dipstick, you're starting to get into the region where the crank counterweights might start actually thrashing into the oil. So, the traditional place to fill in a crankcase is between the marks somewhere, and everybody's talking about how it's right up to the full mark or even a little over. There's no need to do that. There's still plenty of oil if you're between the marks somewhere. A little bit about the fuel tank. In the US and Canada, we have this, in the second gen Prius, we've got this, both gens actually, we've got this rubber bladder in the gas tank. And it's not just a rubber bag, it's actually more like a diaphragm in a barometer or something. It expands up and down pretty much, and the edges are held sort of straight. This is to keep the fuel vapor above the fuel down to reduce hydrocarbon emissions. So in cold weather, it gets a little bit stiff and it's hard to fill. Various stuff about the fuel system, don't really need to go over that. An interesting feature is that the void between the steel outer shell of the tank and the bladder itself, if fuel ever leaks into that, that's bad and we want to know about it. So part of the evap testing involves pulling air from that region, running it through the engine, and testing the ratio of burn with the air fuel sensor. So that's a periodic cycle that happens in the car, and if any kind of increased mixture is detected there, that means there was gas in there, and that throws a code. In the exhaust system, in the classic Prius, we've got this interesting sort of second catalyst. During warm-up, like just right at a cold start, gas comes in, and instead of going straight into the catalyst, it gets shut off by this vacuum-actuated valve, and it gets forced through this hydrocarbon absorber around the outside. So it's something similar to a charcoal filter, but probably a little different. What that does is trap the unburned hydrocarbons from that warm-up run, which is very fuel-rich, in there and not let them out the back of the pipe. Then at the same time the catalyst is warming up so it can get up to operating temperature and actually deal with it. And then later on, not too much later, but the valve opens up and allows full gas flow, and then the hydrocarbon adsorber gets purged, and all those hydrocarbons now go through the catalyst and get treated. So this is to reduce cold start emissions. This is in the classic, of course. It's not in the second gen, and here's why. The other problem with this, in the first gens, this valve is underneath the car. In the salt belt, it gets really rusty. It's part of it runs really hot on the exhaust pipe. One good thing to do to it is probably get under there and try to get it lubricated and keep it work loose. This is something that the car owners can do, but if they're not, an auto tech can help them out with this. In the second gen system, we have an interesting mod of the cooling system, which also has to do with cold start emissions. At shutdown of the car, a separate pump takes hot coolant from around the hot parts of the engine, shoves it off into the storage tank. We've actually got one of these here. Pass this around if you want. This is a vacuum thermos, just like your coffee thermos. There's a vacuum void in here in between two walls. It's copper coated to reduce radiative losses, and it's actually stored, like this with an intake pipe coming up all the way up, so the convection keeps the hot fluid near the top. So what happens is during shutdown, the hot fluid is pumped out, and about 3 liters worth of it are kept in that tank, and it can stay warm for 2 or 3 days, depending on ambient temp and winds. And then at the next start up, this pump shoves all that hot coolant back into the engine, right around the cylinder head and the top of the cylinder walls, right in the combustion area. So now we finally start the engine. We've got a little bit of a preheat right around where it counts, the cylinder walls, because it's a heat engine. We need to have heat in the engine. That immediately reduces those cold start emissions by a substantial factor. So not only does this coolant tank tend to conserve heat in the engine and then feed it back in when you need it, we also get the same benefit of that funny exhaust valve without having the funny exhaust valve.
When my first thought about pouring hot liquid cold into a thermal shock.
Well, yeah, but you're going to get a lot more thermal issues by burning gas inside it. It's totally not a problem. And since it's the coolant, it flows evenly right around the cylinder walls. I can actually watch this. I can watch the pump in happen on my temp gauge in my car. I see it tick up and then it'll sort of slowly start dropping as the heat dissipates off into the block.
Is that Gen 2 only?
This is Gen 2 only.
So the problem with the plugins of having the NOx emissions would have not been an issue with the Gen 1 absorber.
I'm clear. I haven't studied that.
Oh, okay.
An issue with this, of course, is since the cooling system is a little more complicated, the bleeding procedure is a little more complex, and that's something that the mechanics can look up at their data supplies. It sits here under right under the fender. It's like the first thing to go in a frontal collision, so they get whacked pretty often, just like that one did. But even though that one got whacked, it still had the vacuum in it. We might cut it open if we sucked all this air in. So the seal was still intact. It's behind these plastic fender liners, which mechanics love to just sort of like fold out of the way, and they should really be a little more careful about that because they tend to leave creases in it and lose some of the little retainer fittings. That's a blank slide, so that means I have to change carousels here. So that's pretty much about the engine. There's probably a lot more to it, but we don't really have time. On to the electric stuff. And of course, the first thing you think about on the electric side is the battery, and I don't really have to go over any of that because Wayne already did. And if you missed that, he's going to do it again after this. So we're running like sort of twice in tandem here. This was one we were hacking on at the Tour de Sol last year. Service plug wiring, went over all that stuff, charge management. Both of us, he was over at my little setup yesterday out on the Midway, and so we were both answering people that came up, what about batteries? Do I have to replace them? We'd say in unison, lasts the life of the car. And that's like the major point that we have to drive home to the public because they just don't understand. We passed this around, it's still floating around the room somewhere. This shows the 2 interconnects that increase the second-gen packs to 100 amp capacity from 50 or 60 or whatever it was. Numbers, he gave you all that. This is kind of a quiz for the techs, the ones that are like falling asleep at this point. Say, okay, why are we not wearing our gloves to touch this pack? And of course the answer is we've taken the interconnect bars off. And even if these interconnect bars were still intact on the other side of the battery, the maximum voltage we get between any 2 of these lugs would be about 16 volts. So that's safe to touch. That's under the danger level. And again, this sort of shows the serpentine hookup back and forth, adding up all those voltages. Compression rods to hold the thing squished together. In addition to that, not only is the battery pack isolated, but the cables that pass under the car are these weird coaxial things. So there's actually a grounded shield around where the actual battery cable passes in the middle here. And you can see that the connectors into the inverter have a shield around them that's actually connected to the plug, and then inside is the actual terminal for the high voltage. So any part of that gets damaged, it's very likely that it's going to create that ground fault. The cable got penetrated, and that's going to trigger the alarms. Inside the battery ECU, he's pointing out those little taps to monitor the voltage. That still can present full battery voltage into the battery computer. So you still got to be careful when working around in that. At this point, we've introduced the concept of an inverter. And you know, an inverter is a part that most auto techs have never seen before, and they have no idea what it is. There's a whole Motors 101 section on the website, which is a whole separate piece, because most people just don't even want to know about this stuff. Suffice to say that it's a very basic sort of high school science fair explanation of how three-phase motors work. How we apply fields to coils and force the magnet to turn around. We'll someday make a really great animated GIF. And we can sort of synthesize the drive waveforms and get sort of as close to that three-phase power in commercial buildings as we can. But to get all that from the battery, we've got your basic 6-transistor ladder inverter circuit. By turning on transistors in the right order, we can keep that magnet spinning around. So I'm really not going to go into that too much, but suffice to say that there's this large block of power electronics called the inverter with 3 leads down to each motor, and that's what drives the thing. And also it collects power back from the motor during regeneration.
You got this posted on the web?
All of this is on the website as m101.html.
I got guys that ask me questions, and I love this.
Yeah, this is going to be extended at some point too, because there's actually some really interesting modulation of this stuff that the Prius does that I'm still looking into. So, you know, taking my O-scope, cruising on a Saturday night and capturing waveforms. So it just shows the 6 basic steps of commutation. What's interesting is the Honda systems still sort of do this. They have a bit more primitive switching mechanism, and the Prius has gone way beyond this and gets much more motor efficiency out of the thing. So this is one of the like 300 patents that govern the original classic Prius, and you know, here we see our 2 motors and our 2 inverter racks. So there's that whole circuit that we saw before is doubled up in this because we got 2 motors to deal with. Around each motor is a thing called a resolver, and that's a sort of a position detection thing. Tells the control ECU where the motor is at any time and how fast it's going. And the control computer really has to know that because it's got to do all that torque balancing stuff. So it reads those resolver inputs, and it reads the position of the accelerator pedal and the shifter. You know, a whole bunch of inputs go in and does a bunch of math, and then farms out control to the inverter rack and various other things. And it does this many times per second. The computers have gotten fast enough that that's now feasible. This patent is actually a good read because you can look it up at the free patents online or the USPTO. Toyota actually had to design their own semiconductors from scratch because nothing off the shelf in the original design efforts were good enough. They kept blowing them up. In the updated system, we have the same thing: 2 motors, 2 inverter racks. In addition to all that, in the 2nd gen Prius, we've got this thing called a boost converter, and I actually have the coil from it. This is just a big encapsulated, big honking coil. This is what converts 200 volts into 500 volts available at the motors. That represents some creative switching. Not only because it can jack 200 up to 500 in here, it can also regulate charge current back to the battery. So it gives an easy way to keep control of that. The other thing that shows up in the 2nd gen Prius is a whole separate inverter section for the air conditioning compressor. It moves from a traditional mechanical air conditioning compressor hung off the engine to this electric thing. And that takes a 3-phase output straight from the hybrid battery because it has to deal with a lot of power. You can't run air conditioning up to 12 volt, you'd be drawing like 200 amps. Inside the inverter, it's not that much to see. It's a big capacitor module. I have an extensive, so far, 4-part teardown of the inverter up on the main website. Lots of good pictures. That's worth a read. Inside the inverter, between the 2 sections, there is a water cooling loop. So this pink tank over here is a reserve tank just for the inverter and the motors. The power transistors, it's vitally important to keep them cool because if they ever went into thermal runaway and blew up, then you're dead in the water, the car doesn't go. So they run a cooling loop under all this stuff back and forth through a cold plate, and the transistors are all bolted down to that. And then after it's done cooling the transistors, it then goes off to the transaxle, helps cool the motors as well, and it's got its own little separate radiator section in the front of the car. Once we can start getting into the inverter, this is one of the Argonne pictures. Start seeing some power electronics down in here. We see the three terminals of each motor going out on either side. Some details about how it chops does power modulation. That'll all be in those extended pages to the teardown section as they come in. Again, the definition of neutral for this car, that simply removes all control from those power transistors and lets the motors spin free. That's all neutral does. There's no mechanical change in there. On the flip side of the inverter, we have two more sections. One is the DC-DC converter, which takes the 200 volt in, transforms it down, and that feeds the 12 volt bus. And then the separate section for the air conditioning. You can see those 3 wires going out to it. Argonne got a few details wrong in this thing, as far as transistor counts and things. What MG2 looks like, if we had that sitting here and had the end cap off, that's what it would look like. This rotor is about, maybe that deep and get big around. It can produce some pretty beefy torque all on its own from a little 6-inch across thing. And there's some details about the motors. At this point, we're probably into areas that the auto techs don't care about. Another interesting thing is during regen, we can actually have workable regen all the way down to like 8 miles an hour in these cars. And at that point, MG2 is not spinning fast enough to get useful power off of it. But it's also, if you just let it spin and collect the power that it creates, it's nowhere near 200 volts. So to get over that, the inverter switching is actually used in a similar way to this boost coil. As the motor spins, it's generating current. And what the switching winds up doing is momentarily shorting that current, and letting it build up in the motor to create a field, and then letting go. Just like an ignition coil in the car, when you build up current and then suddenly open up the feed to a coil, it tends to generate this huge voltage spike. And if you do that often enough, you can collect the sum total of those voltage spikes. So just like the boost inverter can turn 200 into 500, using the motor windings themselves in that way can turn whatever the motor's producing back into enough voltage to feed the battery.
Which they do.
Which they do.
On the regen at low speed.
Yeah, you can actually hear that. You can hear a high-pitched whine going on when you're in regen. So let's look at what happens when you start up the car. Before you get the, before you sit in it, there's like the smart key going on. There's the mobilizer conversation. To authorize the key. When you come into accessory mode, that first power state, this is without your foot on the brake. You just get to that first thing. A few things power up, no big deal. Then you come to the ignition on state. All the computers boot up, and at this point you can talk to all the computers and get error codes out of them, and start reading parameters and things. The high voltage battery is not online yet. The relays haven't contacted, but since the battery computer is powered up, you can actually read the block voltages and actually get some results from that. And of course, all the other stuff is enabled. You can put the car in neutral here, but you can't put it in drive or reverse. At this point, all of the networks in the car come alive. So all these computers are now powered up. They can talk to each other. So all of this network chatter starts happening across the high-speed CAN bus, and there's actually 2 other slower networks in the car to handle the stereo and various body functions. The main ECUs for driving, and these have to all be online and functional, or the car doesn't go anywhere. The hybrid ECU is sort of the mastermind of the whole thing. It farms off engine run tasks to the engine ECU, and the braking controller is also very integral to this because of the regeneration integration. Of course, the battery has to keep reporting state of charge because many decisions are made off of that. If the CAN bus is down, generally, if the car powers up at all, you'll get all the gas gauge blocks will be blinking, meaning you do not have communication. Wayne went over what happens when you finally bring the thing online. The inverter capacitors are at 0 volts, the battery's at 200. You don't want to just connect them immediately because you'll weld your relays shut. This is an actual trace of that pre-charge stuff, and then it is fairly quick. You hear like click of a click in the back, and it's done at that point. So by tracing voltage and current, we see in the red here we get a little bit of a current spike as we start charging the capacitors, but the voltage slowly comes up to 200. You know, if we did that without that free charge, the current spike would be, you know, up there somewhere, and we'd be destroying things. And also, you can, you know, when you sit in the car, you can hear that, and if you sort of learn that kind of relay dance, what it sounds like, you can tell if the car is working or not. So as we come into ready, finally we get the inverter charged up. The DC-DC converter inside it starts up and starts producing our 12-volt charging. So if you have a voltmeter connected to the system, you can see it jump from 12 volts to 14 volts. And of course, the first thing you hear, besides all that, is the little pump under the hood pushing the coolant back into the engine. That pretty much happens immediately as soon as that gets going. About 12 seconds later, the engine just starts up, and you can be in drive and moving away at this point. The engine will just sort of start up when it needs to. It cranks at 1,000 RPM before gas and spark are applied. And if the engine doesn't actually start and begin producing power, it still sounds like it's running. And that's confused a lot of people because they think that it starts and then it dies again, but it never was running in the first place, if there's a problem. During the first minute or so, 57 seconds, I think Yoshi said, the engine time, the ignition timing is very retarded. The idea here is to actually get unburned gas to run down the exhaust pipe. That helps heat up the catalyst. So the first priority after engine start is to get those cats nice and hot so they can then start dealing with the emissions. This is a period of much higher fuel consumption, of course, because we're dumping a little more gas. You know, the engine isn't fully up to operating temperature, so we have to compensate by making the mixture richer. But it doesn't last that long. But since that's a very controlled state for the engine to be in, the engine is not used to actually push the car yet, unless you really punch it.
So you can override it.
You can override it, but it's not advisable. So what you really want to do is, you know, be gentle on the drive. And you know, if you go at a respectable acceleration, you're going to be drawing a huge amount of battery current. So it's going to draw your pack down really quickly. So what I usually do in my neighborhood, I sort of crawl up that first hill, and by then this initial run is over, and I can go to EV mode and like drift out on the downhill.
What happens if you shift into neutral right away?
The engine will still run.
You'll do this cycle anyway?
Well, here's a trick that the techs can. If the techs who care about the customer's MPG average, if they need to do testing that involves coming to full ready mode, since there's this delay before the engine starts, they can boot up into ready mode, slap it into neutral right away, and that'll prevent the engine start. And then they can power off. And they can do that the 4 times or whatever it takes to clear some error states. So yeah, if you're in neutral, this thing won't happen until you finally shift into drive or back into park.
And then once you're into drive and it started going and you put it back into neutral, you try to increase your early MPGs, does that cut this short?
Well, it doesn't really cut it short. It will complete this process when it can. So keep track of sort of where it is in that cycle, and if you've run in neutral for a while, it'll like go back to that warm-up mode. It's not, in the second gen Prius, it's not a long time, so it's really not much of a hit. Auto shutdown doesn't really happen until you reach 40 degrees centigrade coolant temp, so you can sit there idling at a light during those first couple of minutes. And all of this is documented pretty well by the 5 stages thing that Danny over at Prius Chat wrote up a long time ago, and I managed to scrape a copy off of some page I had saved. So that's worth a read if you want to get more into that. And of course, in the first gen, we don't have the coolant bottle, we don't have the EV mode, but we do have that vacuum valve operation somewhere later. I don't know how long that takes. For the auto tech, if you want to become familiar enough with the car where you can just sort of sit in the thing and listen around you while all this is happening and immediately notice something wrong, you can get familiar with that. And again, like you were saying, if you put it in neutral right away, right after startup, you can prevent that first engine light. So if all you want to do is clear some codes or something like that, or talk to a computer, that's one thing you can do. Okay, so now we're started up and things are getting going. What happens when we actually put our foot on the pedal and go? If the techs haven't been paying attention, they may still not know that you need to put your foot on the brake to get out of park. When you get out of park, in the second gen Prius, you don't do that by a mechanical linkage like pulling the old lever down. There's this electric actuator motor This is actually a little three-phase unit, very similar to the motor generators, but much smaller. It's got these little sensors in the bottom that detect whether or not the thing's spun. So that's how the car knows whether this little thing is active or not. This passes through a 60-to-1 reduction gear, which is an interesting little sort of cycloid drive that advances 1 tooth per full rev. The reason for that is if you ever parked on a hill and then took it out of the park, you feel that thunk in the release. It takes a lot of force to pull the parking pole out from a gear that might be under a lot of heavy load with the car sitting against it down a hill. But this happens really fast. I mean, in the second-gen Prius, you go between park and neutral, and you can hear that thing just kind of go, and it's done. Again, it's a full three-phase motor driven from a separate ECU that handles it. So finally, we want to go. The accelerator pedal is all drive-by-wire. All that is a request to the ECU by a couple of voltages that we want to make the car go faster. In the first-gen Prius, it was a dual-wiper potentiometer, which started to go flaky after a while, and it gave what's called big hand syndrome. So you'd be pushing the pedal, and the car just wouldn't be going, simply because the wipers in that variable resistor had started to flake out. And Doug Schaefer, for a while, was actually fixing these, cleaning them up, opening them up, and like re-epoxying them shut, and doing this sort of exchange basis fix-up. In the second gen, we moved to a sort of thing with Hall sensor ICs and a couple of magnets that turn over it. So it's a complete non-contact system. It should never wear out. So that's an improvement they did. Again, it's two outputs. They self-check each other. If one of them suddenly goes weird, the ECU knows about it and can light an error code. So again, the ECUs do a whole lot of math. So so part of what it does is a small subroutine. These N's here are kind of an interesting thing. N is a sort of engineering representation of rotational speed, usually given in radians per second, and that eventually translates to RPM. So N sub E is revolution speed of the engine. Knowing that, if anyone wants to try unscrambling this alphabet soup here, any as our engine speed comes to the engine controller, like from the cam and crank sensors. What it does is sort of clean that signal up and give a direct copy of it to the hybrid ECU. And the reason being, the hybrid ECU not only wants to know how fast the engine is going, but exactly where it is. But by knowing the engine position during shutdown, the electric motor. But by knowing the engine position during shutdown, the electric motors are used to actually position the engine about 9 degrees before the next top dead center, so that it knows exactly where the engine's going to be during the next light off, so it doesn't have to wait for it to go around a couple of times before it can determine its zero position. So right away, it can just start feeding gas and spark to the right cylinders very quickly. Of course, the exact algorithms in here, you can read the patents till you're blue in the face, and you can participate in Prius Tech Yahoo group, and all of this is really a lot of unknown stuff, guesswork, that's just locked deep in the vaults of Toyota. But people have made good progress in guessing a lot of these algorithms and how they work. Some of the industrial control guys do this for a living in other contexts, and they can take good guesses at it. There are lots of different thresholds and state of charge and road speed. Just numerous factors come into play here.
So bottom line there, if you have a 10-horse electric motor.
You've got a 50 kilowatt.
No, but in terms of your previous last point, is that...
I have 5 minutes. In this audience, I can talk about efficiency. This slide is pretty useless to the auto techs because they don't really care about this. They wanted to hear about the guy with the boat that burns 45 gallons of fuel an hour to carry his drinking buddies around the bay. But this is from an SAE paper discussing Prius throttle control. And bottom line is it's sort of a fuel consumption chart. You'll see the numbers get bigger down here. So if you're running at high RPM at low torque, you're in a very inefficient region. You're sucking a lot of gas for no output power. And this is kind of like a contour map, a hill on a contour map. What you really want to do is be operating up here as much as possible. The way to get there is to start at a very low RPM and bring up the shaft load on the engine, get it into a high torque mode by opening the throttle fairly far, right off the bottom line. And that's what divorcing the control of the user's foot from the throttle gives you. You get you're able to just sort of climb your way up that hill right away, and everything else from there on is all about RPM. So this is why, as you put your foot down on the Prius and you're on the highway, you hear the engine rise up and down, but the torque load is pretty much stays the same. It comes right up to 80 Newton meters, and it's pretty much stays constant through this whole RPM range. And that's the essence of pulse and glide. With pulse and glide, we want to be either all the way off or like high on that curve right away. We just sort of alternate between those two states. So here, you offer a quiz to the techs. Here I am going 66 on the way to Hybridfest last year, turning 1800 RPM. Where's MG1? What is MG1 doing? And they scratch their heads and see if you remember what MG1 actually is. And since RPM is governed by this, to upshift a Prius, you back off your foot and let the RPM drop, and you're still under a good shaft load. So to figure out the answer to that question, you go back to the nomograph. And it's pretty much matches the red line. You've got engine RPM, somewhere around 1600 or whatever. You're going a respectable highway speed. MG1 is spinning backwards, except that since the engine is torquing forward and the car is moving forward, how the heck is MG1 spinning backwards? The answer is it's drawing power from the big electric motor, MG2, sending that power back the other way through the inverter and pushing MG1 backward as a motor. This is how we get overdrive in a Prius. You have to take up torque actively pushing the other way against the engine. But that keeps its RPM down and under control, and turns out to be a more efficient state. And then we get the techs up out of their seats again, they go explore the cars. And then, of course, the braking system is one of the most complex aspects of the car. The braking ECU is located over your legs when you're sitting in the car. You can also see the diagnostic port. Skip all that. The first thing that happens when you ask for braking generally is a network conversation between the hybrid controller and the braking computer. How much counter torque can you give me? And the hybrid controller answers, meanwhile starting the regen process, which may or may not be the same number. If you exceed the 100 amp regen limit into the battery, the braking computer has to take up the slack by starting to apply hydraulic pressure. So it handles the excess, and it brings in the rear wheels first, generally for balance. And all the way down to 7 or 8 miles an hour, like I said. The hydraulic system looks like this. During normal operation, these two solenoids close off the lines to the rest of the wheels and things. And everything else happens electrically. Braking pressure actually comes from this high-pressure accumulator. There's a pump motor that runs up about 2,000 psi and stores it in this high-pressure nitrogen cylinder, keeps track of it. And the actual braking request is read from these two pressure sensors into the braking ECU, which then, if you need braking pressure, starts controlling these apply and release solenoids for each individual wheel. That's how brake balance is done. Full ABS functionality is in this. So normally the user's foot is, again, sort of decoupled from what's really happening. There are a couple of backup systems. If the whole system goes down, these two solenoids open up and you've got a direct hydraulic path to the front wheel brakes. So you can actually still brake the car when it's not powered up at all. There's kind of a lot more to this, but I think I'm out of time at this point. One interesting thing about the braking system is that if you do a panic stop, that conversation between the two ECUs about regen doesn't bother happening, because now that's a safety situation. You just have to stop the car. It just starts grabbing the brakes right away. And it's not an all or nothing thing. That you can sort of do a mix of that. Here's part of another backup system in the brakes. It's got its own little power supply. Some capacitors that store a reserve amount of power just for the braking ECU. So between that and the high pressure accumulator, it's sort of like that vacuum boost thing. You get a couple of good cycles of assisted braking out of that until all of that finally goes dead. So if you lose your 12 volts entirely, this can keep the braking system alive to get you to the side of the road. And then after that direct hydraulic path would kick in. So if the pressure sensors or any other part of this goes bung, it makes a couple of bad assumptions. But careful study of this, if you're going to work on it at all, is just really worth it. A couple of safety things. If the tech wants to work on the brakes, you should really disable that high pressure accumulator. Pulling these two relays will prevent the pump from running, and it's actually an advised service technique in the manuals. There's various little dances to recalibrate this whole system. You can launch with a scan tool, and you really need to let those finish up and definitely return, I'm okay to you. If you power off in the middle of that, it'll go into this unset state and you won't have any regen braking at all. So the customer comes in and starts complaining about various things like, why is my MPG suck? Make sure their brakes are actually working right. And of course, the usual complaint on the forums is the brakes were being grabby, right? You're on regen all the way down to a certain transition point, and if your rotors are rusty from sitting out on a wet day, suddenly it's like grabbing sandpaper and the car falls on its face, and a lot of people don't like that. The trick, of course, is just pop it into neutral, which disables regen because you can't use the electric motors, and just do a nice, gentle, even braking from a reasonably high speed to scrub all that stuff right off, and they'll work right again. Interesting diagnostic thought. If I'm trying to track down a clunk that I hear when I'm braking, the hybrid-aware tech will say, well, is that during regen or physical braking? Because different parts of the car are going to be taking that force. The customer's answer will generally be the third line, but you might have one of us that's in there and say, oh yeah, it's definitely during when I transition to physical. The rest of this is all about 12-volt crap with the stuff here. The lights.
Yeah, what I'd like to do is, I want to make sure everyone has the opportunity to do the hands-on.
Yeah.
So Wayne doesn't need the card. If we could just set everything on the card, we could go into another room or something. Or we have about an hour.
Do we have another